talking about state expiration. The game plan for today, first we'll begin by defining what the problem is, state bloat, and how it affects not only the Stellar blockchain, but all blockchains as a whole. Next, we'll go into the developer interface, which is the tools that you Soroban contract developers will need to use in order to take the best advantage of our state expiration features. Then we'll go under the hood and dive into the implementation details and see how this actually works in a core validator. And finally, we'll conclude with a rollout and how we're going to launch this when Soroban mainnet hits later this year. So what is state bloat? First, let's define state. So on a validator, it must store all the information of the network. These include things such as trust lines, balances, accounts, contract code, smart contract instances, all that information that validators need to make the network run. All validators must store this locally on their system. Consider the transaction where I send Sally 10 XLM from my account. In order to validate that transaction, the validator must first load my account balance, verify that I actually have at least 10 XLM on it. Then it must load Sally's balance, and then remove that 10 XLM from my account and add it to hers. Then it writes the result back to the ledger on the local hard drive. So that's what state is. Now, what is state bloat? So state bloat is all of the data that validators need to store, but that's not actually used on a daily basis or very often. So earlier this morning, I actually went on Stellar Expert and looked at a couple of assets that are currently live on Stellar, but aren't frequently used. Those examples include Garlic Coin, Mini Shiba Inu token, not to be confused with Shiba Inu token, and then Peppa the Pig coin, which are currently live on Stellar. Now, as you can see here, the amount of state that we have to store has increased exponentially over time. Additionally, with the introduction of Soroban, we expect not only the number of these entries to continue to increase, but the size of these entries to increase as well, further amplifying this issue. So before we actually find a solution to state bloat, I think it's important to first understand the root causes as to why state bloat happens. And so we have, at the Stellar Network, is a public blockchain, which means that anyone can submit a valid transaction. Now, each of these transactions takes some amount of computational resources of the network. And so, in order to make sure the network is fair for everyone that's using it, we charge resource fees for each resource a transaction consumes. Like Sid was talking about earlier, you have things like CPU, memory, storage, all of these fees. Now, these ensure that the network is both fair, that you're paying for what you're using, and it also is a protection measure for things against DOS attacks, where one transaction could potentially take up all the resources on the ledger and not allow any other transactions to execute. But the fundamental issue is that when it comes to storage fees in particular, the storage fee system on both Stellar and all other public blockchains is fundamentally broken. So how is this broken? So on the right, you can see here that we have the diagram of a validator. And we have the three different resources: a compute resource, a history archive or a network resource, and then finally our database resource. And let's consider the transaction where we mint one mini Shiba token at our address 0x123. So whenever we submit this to the network, we will then have to pay a small fee for each of these resources we consume. First, we might have to do a signature check, which requires doing some math to make sure that the issuer of this transaction is allowed to mint Mini Shiba tokens. And so we're going to be charged for doing that computation. Next, we have to record that this event happened. And so the validators will need to send some network traffic to the history archive. And so we're charged for that network traffic. And finally, once we mint that token, we then need to store that balance on our validator hard drive. And so we're charged a fee for that write. And so we see that this transaction goes through, and we're left with our one Mini Shiba token balance stored on our validator. The fundamental issue is these are one-time fees, but we have to perpetually store this token balance forever. Now, for compute and for the network fees, the one-time fee is fine. Once your transaction gets executed, you're never going to have to submit network traffic again, and you're never going to have to use the CPU again. But storage is a different situation. So as you can see, we're just going to keep submitting transactions. And even though we're charging a one-time storage fee, we have to continue to indefinitely store all of these tokens, some of which are frequently used, and others which are less frequently used. There's no end in sight. This increase continues to go and go and go until eventually we run into some significant issues, and the validators just can't keep up. And so the foundational issue with state bloat is the problem with storage fees. We have a one-time storage fee charged, but this one-time fee, there's a reoccurring perpetual cost on the network because the storage must be stored indefinitely. This comes first in an operational cost. Because validators need to have larger hard drives and larger databases to maintain all of this bloat, it's more expensive for operators to run this, as if they're running something on AWS or on the cloud, they need to spend more money for IOPS every month, or if they're running a local device, they have to spend more money on bigger and faster NVMe drives. In addition to the operational cost, there's also a network performance cost. As the larger your database is, the harder it is to maintain and the slower it is. So the number of transactions and the speed of transaction execution decreases. And so since the fundamental issue is that of a fee mismatch, our solution at its core is just adjusting the fee structure. Instead of charging a one-time fee, we are going to charge a reoccurring fee for every entry on the ledger. What this looks like is that for every ledger entry you store, you must continually pay rent. If you forget to make rent payments, then your entry is considered to be expired and is permanently deleted. Now, this interface just by itself is terrible. Consider you have a balance that has like 1 million USDC tokens in it, for example, and one day you forget to pay your rent. That entry would be expired and then permanently deleted, which means you would lose your 1 million USDC permanently. We obviously don't want that to happen. So even though if you forget to pay rent, your entry will expire, we also offer a restoration mechanic, where if you do forget to pay rent, you can restore an expired entry and bring your 1 million USDC tokens back to live on the network, and so your balance is not permanently lost. So we'll get to questions at the end, thank you. So that's the high-level solution. And so let's talk about some of the details and to the actual developer interface we've exposed and how you can take advantage of these features in your smart contracts. Let's begin with some terminology. So in Soroban, every entry has a lifetime measured in ledgers. On every ledger close, this lifetime is decremented by 1. When I say every Soroban entry, this includes contract data, but also contract code and the contract instances themselves. Whenever the lifetime goes to 0, the entry is considered expired. And an expired entry cannot be used by any transaction. To be specific, if you have the key of an expired entry in your transaction footprint, that transaction automatically fails before it even has a chance to get applied. Now, if you don't want your entry to expire, then you can issue a lifetime bump operation or use the lifetime bump host function in order to extend that lifetime so it doesn't expire. But if you forget to issue this lifetime extension, you can always make your entry live again via the restore operation. So those are our terms. Let's go through an example to see how this works in practice. So for our example, suppose that we have a contract like USDC, and Circle has used Soroban to implement this. On our first ledger, ledger N, we're going to begin by submitting a transaction to create a new USDC account. And so here we see we have our newly created USDC account, we have our account ID, we have a balance that's initialized to 0 because we just created it, and we also have this new lifetime field. In Soroban, whenever you create an entry for the first time, its lifetime is default initialized to the network default. In actuality, this is much longer than 10 ledgers, but just for the purposes of this demonstration, let's suppose it's 10. So 1 ledger passes, and as we see, our lifetime is decremented by 1 to now be 9 ledgers. And let's say that on this ledger, we submit another transaction to deposit 10 USDC into our account. That transaction goes through, and we see our balance is updated. Now a few more ledgers pass, and we see that our lifetime goes to 0. Now because our lifetime is 0, our entry is now considered expired, as you can see by this dotted red line. Now on this ledger, we attempt to make another deposit into our account and deposit 15 USDC. But because our entry is expired, this transaction will fail, and our balance will remain at 10. Note that you don't lose the 15 USDC. It's not gone into the ether, it's just that the transaction fails and doesn't go through. So we've learned from our mistake, and now we know our entry's expired. So on the next ledger, we are going to issue the restore operation. Now note that whenever the next ledger passed, the lifetime did not go negative. Once your entry is expired, the lifetime is capped to 0. Now we issue our restore operation, and then our entry will now be restored to be live again. Note that whenever we issue the restore operation, our lifetime is again default initialized to that network limit of 10. Now, 1 more ledger passes. You all know the drill by now. Our lifetime is going to be decremented by 1, and we've learned from our mistake. And so, in order to make sure our entry doesn't expire again, we're going to issue the lifetime extension operation, which is going to then increase our lifetime to 150 ledgers. So that's basically the picture. Now let's go into some of the details, the specifics of these operations. So we have 2 operations, the lifetime extension operation and the restore operation. These are both Soroban operation types, which means they must have a footprint and follow all the other Soroban limits. Note that no authorization is required for either of these operations, which means that any account can issue a lifetime extension or restore any entry with no authorization checks. So first we have our lifetime extension entry, or our bump footprint expiration op. This takes a ledgers to expire parameter. What this function is going to do is it's going to iterate through every entry in the read-only set of the footprint, and then if that entry's lifetime is below ledgers to expire, it's going to increase the lifetime up to ledgers to expire. Now, if an entry already has a lifetime that's greater than the parameter ledgers to expire that we passed, that entry is just skipped. And so you're not going to be charged any fees, and the entry is going to remain unchanged. Speaking of fees, like Sid mentioned earlier, we charge a rent fee for lifetime extensions. This rent fee is based both off of the size of the entry being bumped, as well as the number of ledgers that you're bumping the lifetime to. This just follows an analogy like an apartment. You'd expect to pay more for a 3-bedroom, 2-bath apartment than you would for a studio, so we take into account size. And it costs more to have a year's worth of rent in your apartment than it does to have a month's worth of rent of your apartment, which accounts for the ledgers. Now, in the terms of Soroban fees, lifetime extensions and rent fees are some of the cheapest fees and are much cheaper than write fees. Next, we have our restore operation, or the restore footprint op. What this will do is iterate through every entry in the read-write set, and if that entry is expired, it will restore that operation and make it live. Similarly, if a key in that set is already live, it's just skipped, it remains unchanged, no fees charged. Like I mentioned in the demo earlier, whenever you restore an entry, its lifetime is again default initialized to that network limit. But unlike the bump expiration footprint op, this operation is significantly more expensive when it comes to fees. Whenever you restore an operation, from a fee perspective, that's just as expensive as if you were recreating the entry for the first time. Now, what this means concretely for you developers is that it's much cheaper and economically viable to periodically issue bump expiration operations to maintain the lifetime of your contract or your entry, rather than letting it expire and then having to issue a much more extensive restore operation later on. So here's kind of our two key primitives here with the operations. Now, lifetime extension is pretty self-explanatory. You should know how to manage your own lifetime rent. But when do you know when to issue a restore op? How can you tell if an entry is expired or not? So we've built a tool just to do that in Soroban RPC. So Soroban RPC has a simulate transaction endpoint that can be used in order to tell if your transaction touches any expired entries. The flow looks as follows. So first, you're going to submit your transaction to the simulate transaction RPC endpoint. That will then return a JSON payload. A field in that JSON payload is called the restore preamble. If there's an empty restore preamble, this indicates that your transaction does not access any expired entries, and so you should be good to go. You can go ahead and just directly submit that transaction to the network. However, if that restore preamble is non-empty, that indicates that the keys in that restore preamble have expired and your transaction needs them. So before you actually submit your transaction to mainnet, you will need to take those keys, attach them to the footprint of that restore operation we talked about, and then submit that operation first. Then, once you've submitted that operation, your entries will be considered live, and you can go ahead and submit the original transaction to the main network, and it should work because all the entries it touches have now been made live. So we have an operation for restoring and an operation for lifetime extension. In addition to this operation, we also allow smart contracts to define lifetime extension behaviors natively in the code. To do that, you can use the bump host function. The bump host function interface looks as follows. First, it takes the key that you're bumping, the ledger entry, then a low expiration watermark, followed by the high expiration watermark. All this does is if the current entry's lifetime is below that low expiration watermark, it will be increased up to that high expiration watermark. So say I want to bump an entry with the low expiration watermark of 10, high of 100. If the current ledger entry lifetime is 9, the entry will then be bumped up to 100 ledgers. As far as fees, these pay the same inexpensive, cheap rent fees as a lifetime extension operation. So we have two different interfaces you can use. You can either define lifetime extension operation, or you can use the lifetime extension operation on its own, or you can define this behavior in the contract itself. So when should you use one versus the other? Here's some general guidelines on when to use an operation versus defining lifetime directly in the code itself. So let's talk about first the contract code and the contract instance itself. As remember, both the code and instance are subject to expiration and might expire and have lifetimes of their own. First, let's talk about what I call an owned contract. an owned contract is a smart contract that has some central admin authority. For instance, the USDC contract, the owner would be Circle. If you have an owned contract, it's recommended that the owner of that contract periodically use the lifetime extension operation to maintain the lifetime of both the contract instance and code. This essentially is just an ease of use feature to allow your users to not have to worry about the lifetime of the contract entry itself. However, if you have a decentralized application, a dApp, that has no admin, then it would be appropriate to use the bump host function to actually encode lifetime extension behavior in the contract itself for the code in the WASM. What the dApp developer could do is say on every invocation, just do a small bump to the shared resources, such as the code and the instance. This way, whenever the dApp is invoked, every invoker of that dApp pays a small fee towards the overall shared resources. In addition to the contract instance in WASM, if you have any sort of meta information, then that should also be covered by the lifetime extension operation in the own contract case, or again by the bump host function in the dApp case. Finally, if you have an own contract, it might also be useful to use the bump host function in order to maintain relatively reasonable minimums for user state. For instance, Circle may program their smart contract such that every time you access your balance, the lifetime is bumped up to at least 1 month. This is just an ease of use thing for the invokers of the Circle contract because they would not have to manually manage their lifetimes. Finally, if you are some sort of super user and you have needs that are not defined by the contract developer, you can always use the bump footprint expiration op in order to manage state of the entries as you desire. So we've gone over the general lifetime, expiration, all this sort of things. Now there's one other key feature of state expiration that I'm really excited about, and that is the different types of data that we have in Soroban. So we have 3 different data types, and you've heard about them today already through some of the demos. First, we have shared data, also known as instance data. Then we have persistent data, and finally, temporary data. So let me go through the differences between these 3 types and give some examples on when you would use one versus the other. So first, instance data contains all the shared state of a contract. So by default, this is the data that's used by every invocation of that contract. It's not specific to one user. This always contains the contract instance and the contract code itself, but also a small, fixed-sized, arbitrary key value map that you can use to store any entry you want. Some recommendations as to what we would put in this are things like an admin entry, meta information that's necessary for every contract invocation, things of this nature. Now, like I mentioned, it is a small fixed size, which makes it not suitable for user state. Additionally, all of this information lives in a single ledger entry and has one singular shared lifetime. This is very convenient because it means that the lifetime and the expiration state of your contract code, contract instance, and other shared data is always tied together. So you'll never be in a condition where you have a contract instance that's live, but the code it requires is expired. They share one lifetime. Finally, instance data is relatively expensive, but it can always be restored if you forget to issue those expiration extension operations. Next, persistent data. So persistent data, unlike shared instance data, is appropriate to be used by is appropriate for user data. Some examples include balances, nonces, NFTs, etc. This is appropriate for any user state that you need to keep around for a while or that's valuable. This has an unlimited amount of storage, so you can have an arbitrary number of these entries, making them appropriate for user state, and each entry has a separate lifetime. Finally, similar to our instance data, this is relatively expensive data, but it can always be restored if you forget to bump it. Finally, we have temporary. Now, like the name suggests, temporary data is appropriate for data that you either only use for a small amount of time or that's very easy to recreate arbitrarily. A few examples of this can be price oracles, signatures, inputs to a ZK rollup, KYC information, things of this nature. Similarly to persistent, you can have an arbitrary number of temporary entries, and they each have their own separate lifetime. But the crucial distinction is that with temporary information, it cannot be restored if it's expired. You can still use the same lifetime extension operations and host function to maintain the lifetime of temporary entries, but if it expires, it's gone forever. This means you wouldn't want to store something like a balance or an NFT in this because it could be potentially lost. But for information that you only need for a short period of time, this offers a much cheaper alternative to persistent entry, as because of its self-delaying nature, it has the cheapest rent fees of the Soroban network. That's kind of a high-level overview of the interface that you developers will need to deal with state expiration. Now, this next part talks about how it actually works at the core level. Unfortunately, I don't have a ton of time to go into this, and it's a little complicated, so this will be a high-level overview, but I'll be ready for questions out back. Also, if you're just a developer and you don't really care about how core works, this isn't super crucial for you, so all the important information was in part 2. Without further ado, let's get into it. So we've talked a lot about lifetimes, restoration, expiration, all this sort of stuff. But the whole point of this was actually deleting information off the validator. So how do we do that, but still allow it to be restored and recovered later? Introducing the expired state store, or the ESS for short. So the ESS is an off-chain storage node, kind of similar to an L2 like Horizon. Whenever an entry expires from the core validator, it is permanently deleted from the ledger and then sent off to this off-chain L2 storage system. Whenever you need to restore an expired entry, first you must pay the ESS and retrieve the expired entry from this ESS system. You then take the node or the entry you received from the ESS and attach it to the restore op, and then send the restore op back to the validator. Then the validator will receive that restore op, see the entry, and add it back to the ledger, so it can be used again. So here's a simple diagram of how it works. On the left side, you have our validator that has all our live entries stored in it. Whenever an entry expires, it gets deleted in a process we call eviction, and then kicked back to the ESS, which is our off-chain L2 system. This then stores all of our expired entries, and then whenever you want to restore something, you pay the ESS, get the entry back, and then give it to the validator via this restore operation. Now, this is a very simplified picture of the ESS, but we're going to flesh it out as we go, given a couple of security requirements. But I think it's most easy to understand as starting with a simple picture here, then adding complexity as we go. So what are the security requirements? Well, first, we need to make sure that the restored entry contains exactly the same data that the entry had when it expired. Consider the USDC example where I have my balance that has 10 tokens in it. Say my entry expires and is sent to the ESS and deleted from the validator. A Byzantine ESS node could say, instead of giving you the legitimate entry that had 10 tokens in it, lie and say, ooh, I actually had 1 million tokens in my balance. The validator doesn't know what's in the ESS, so it has no way of proving that that's incorrect. So we need to structure our ESS in such a way that this cannot happen and that you can always be sure that the entry being restored is correct. We're going to accomplish that using a Merkle tree. And so instead of just storing our information in this arbitrary key value store, we're going to use a Merkle tree, and instead of just attaching the raw entry to our restore operation, we are going to attach Merkle proofs such that we can verify the entry being restored is correct. So we're going to take our simplified picture here and turn it into this. So it's the same process as before, but instead of our key value store, we now store our information in this Merkle tree structure. Similarly, our validators now store the Merkle root. This is important such that the validator can verify that the proofs that are coming from the ESS are correct. Again, this is necessary because the ESS is an off-chain system that does not participate in consensus. And so through consensus, we can validate the context of our validators, but we have no way of ensuring that the ESS is correct without this sort of proving system. So we've solved requirement number 1. Now we can't lie and say you really had 1 million USDC when in actuality you only had 10 that expired. But by using this Merkle tree, we've now introduced a new issue. And that has to do with proofs. And so whenever you change a Merkle tree, every proof that has been previously generated is invalidated because any change to a Merkle tree changes the root hash. This is an issue for us. Because we change the Merkle tree and add an entry to it whenever something expires, this Merkle tree will be changing on every ledger close. Now in Stellar, a ledger close is 5 seconds, which means in the current system, a person who wanted to restore an entry would only have 5 seconds to ask the restorer or the ESS to get the expired entry, take that proof, attach that proof to the restore operation, and then send it to the network. This is clearly way too tight of a time envelope for this sort of complex operation. And so we need a way in order to make it such that our Merkle tree proofs are stable and don't have to be constantly restored and create this database and CPU churn. So to do that, we're going to change the structure of our ESS. Instead of having one big Merkle tree that changes every time you add an expired entry to it, we're going to break the ESS into a series of small, immutable Merkle trees. This process, however, is a little bit involved. So how do we actually break our ESS from one big Merkle tree into a couple of small ones? So we're actually going to move the Merkle tree, at least part of it, into the validators. So how this is going to work is at the start of every calendar year, the validators are going to generate a new empty Merkle tree that they store locally on disk. Then, throughout the calendar year, whenever an entry is expired, it will not be immediately sent to the ESS, but instead the validators will store it locally on the Merkle tree they're currently building. At the end of the calendar year, this tree is considered constructed, at which point the tree is sent to the ESS. At this point, the ESS contains the complete and now immutable tree that was created during that calendar year. So our validator will store only the Merkle root of that tree, but throw away all the rest of the data because the ESS has it. By saving the Merkle root, they can validate the proofs from the ESS, but they don't actually need to store the data anymore. At this point, we now generate a new empty Merkle tree for the next calendar year and restart the process over again. So going back to our diagram, we have this picture here, and we are going to now transition to this. So here we have a multiple Merkle tree setup where the ESS stores the previous year's immutable trees. And we also have the validator storing the old roots of those immutable trees. Now the validator has the current year's hot tree that builds throughout the calendar year. You may also notice that we removed the eviction edge, because whenever an entry is expired, it is deleted from the ledger, but then added internally to the local Merkle tree stored by the validator. So this is the general picture of what the ESS looks like, but we have one more detail that we need to add. Consider I have an NFT, and I'm going to mint my NFT under my name at my given address. Some time passes, I forget to pay my rent, and the entry expires and is deleted and eventually makes its way into the ESS. Now say I have an attacker who wants to steal my NFT. What they're going to do is they're going to go to the validator and say, hey, this NFT doesn't exist, so I'm going to recreate the NFT, but instead of having my account ID, the owner is going to be the attacker. The validators have no way of knowing what's in the ESS. So from the validator's perspective, if the entry expired, say, 3 or 4 years ago, it's not in the ledger, it's not in the current year's try, and so it's just going to say, oh, this NFT doesn't exist, and it's going to remint it and give it to the attacker. We obviously don't want this to happen, so we're going to add one more requirement to our system. And so we're going to require that if an entry is expired, it cannot be recreated, and you must restore that entry. We cannot allow recreation of expired keys. To accomplish this, we are going to require a proof of non-existence whenever you create a new entry. And so in this system, say I'm creating my NFT and it really doesn't exist. In order to prove that, I'm going to go to the ESS and request a proof of non-existence. The way we've structured our Merkle trees, we use a try system, and so they can provide both proofs of existence if the entry actually exists, as well as proofs of non-existence if the key doesn't exist. We're then going to take that proof and attach it to our transaction, send the transaction to the validators, who will then create our entry and validate that, yes, the NFT really hasn't existed before. But this is a really slow process. Now, whenever you create a new entry, you have to go to this L2 system, have an expensive proof, and go through this process. We don't want that. And so we're going to essentially have an expired key cache inside of our validators via a Bloom filter system. What this will do is that the validators will store a Bloom filter of all the keys that are expired in the ESS. Now, the Bloom filter is a probabilistic data structure, which means that there's some amount of false positive rate. What this means is that occasionally, the validator will think a key is in the ESS when it really isn't. What this looks like in practice is that for the majority of the time, we can essentially generate these proofs of existence locally without going to the L2 service. So we can have the advantage of proving that the NFT doesn't exist without actually going to the ESS and getting that proof. So this is our system, and this is how we can remove state from the ledger, but still maintain its integrity and still restore it later on. So what are the benefits to the ESS system and state expiration as a whole? So I talked about removing state bloat and actually deleting entries. But the issue is we're not actually deleting a lot of the information. We're just moving it from the validators to this other system called the ESS. So why is all this complexity worth it if we're still storing the bytes? Well, it's worth it for a few reasons. So first, ESS node operators can choose what data they store. Because we've structured it in this immutable try method, the ESS operator can choose to only, say, store the last 2 years of archived information instead of storing 10 years of state bloat. so we can reduce the amount of state we store or shard it through multiple nodes. Additionally, ESS operators can also choose to only service certain types of data. For instance, it's possible that Circle will want to run an ESS node in order to provide proofs, but their ESS node only stores USDC balances. In this way, if you have a sophisticated smart contract application, they can self-serve their ESS nodes so that their users do not have to go and buy these proofs from other L2 systems. So we can store only specific data to reduce our computational complexity. Whereas if we stored all this information on the validators would always need to store everything no matter what. Next, because proofs never expire, the ESS nodes can take their time generating these proofs. This means that unlike the validators that need fast NVMe drives in order to close ledgers every 5 seconds, the ESS nodes can use much cheaper and slower hardware because they can take their time in generating these proofs. If your entry's been expired for a year, it doesn't really matter if the proof takes 2 seconds or 10 seconds to generate. So we can use slower hardware that has larger storage capabilities. Finally, the ESS is a completely off-chain system that does not participate in consensus, but via this proof system, it's still rooted in on-chain security. This means that from a decentralization standpoint, as long as our main net validators are sufficiently decentralized, we can have significantly fewer ESS nodes, but still maintain full decentralization. So that's how state expiration works. We have our interface, we have our implementation. When are we launching this? So when Soroban initially launches, it will have the full developer interface. You'll have to deal about lifetimes, you'll have to do expiration, restoration. All of this will be baked in at launch. However, expired entries will not yet be deleted, and we will not yet have the ESS nodes. The reason we're doing this is we need some time in order to get more community feedback and understand this ESS system. Even though we have the general high-level view of what the technology looks like, we still need to solve some issues as far as how do you pay for proofs, what does the proof submission system look like, things like this. But by launching the interface from day one, we can guarantee that every contract deployed on Soroban will be compatible when we launch the full state expiration solution later. And so a future protocol upgrade will introduce the full ESS and then actually begin deleting state from the validators. So thank you. I don't know if I have much time for questions, but I'll be available in the back if I can't take anything here. Also, in case you want to learn more, we have lots of Soroban documentation about all the developer interface, as well as a CAP where we go into the full detail of the ESS and how all this stuff works at the core. Thank you very much.
Thanks, Dan.